Hello, my name is Brij, and I'm here to present our Interspeech paper, Design Choices for X-Vector-Based Speaker Anonymization. First of all, we would like to classify the existing methods for privacy protection in speech into four broad categories. The first is deletion, where the sensitive segments of speech are physically removed and replaced with a placeholder signal. Second is encryption, where cryptographic methods such as homomorphic encryption are used to encrypt the speech signal and then secure the transmission channel. Third is distributed learning, where the speech data is divided across several different machines. The relevant information is computed locally and then aggregated to train the model. And finally, anonymization, which is the focus of this paper. It aims to suppress the personally identifiable information in speech signal while retaining other attributes such as linguistic content, emotions, etc. Now on the screen, you can see the schema for the anonymization framework, which is being used in the first voice privacy challenge. The schema can be divided into three different steps. The first is feature extraction, where we extract pitch, bottleneck features, and X vector from the input speech. The X vector represents the speaker's identity. Hence, in step two, we use the design choices which we proposed to anonymize the X vector. The resulting X vector replaces the original X vector, and along with the bottleneck features and pitch, in the third step, it is used to synthesize the anonymized speech. Now, let us look at our approach. We ask three basic questions which lead us to explore the design choices in speaker anonymization in this paper. The first question is that what is the appropriate distance metric between speakers? Second is, how do we select large number of pseudo speakers from a small pool of speakers? And finally, how do we ascertain that the design choices that we are deciding will result in high privacy and as well as bearable loss of utility? We will try to answer these questions in this presentation. So to answer the first question, we compare two different distance metrics in X vector space. First is cosine measure, which is already used in the previous studies. We will try to compare it with the PLDA affinity metric, which is defined as the log likelihood ratio between the probability that the two X vectors belong to the same speaker versus the probability that they belong to different speakers. To answer the second question, we propose two design choices: gender selection and proximity. Gender selection is the method which attributes a gender identity to the target pseudo speaker. It can be same as the source target speaker. It can be opposite to the source, or gender selected at random. Second is proximity. Proximity is the precise location where we map the target pseudo speaker. For that purpose, we identify certain regions in the X vector space, such as dense or sparse regions, or it can be relative to the source speaker, like near or far from the source. After selecting these regions, we select n star X vectors from this region, and then we average these X vectors. Now, some of you might be wondering whether if we average the X vectors which are in opposite direction relative to the source, it might result in a X vector which is close to the source. We will try to also answer this question in due course of time. Now, to answer the third question, that how do we ascertain whether these design choices actually perform well in terms of privacy as well as utility? First, let us look at the privacy evaluation. We adopt the attacker's model to evaluate the privacy, according to which the attacker possesses certain enrollment data and also knows the speaker's identity in the enrollment set. The attacker then uses this data to conduct trials with the publicly released test corpus and tries to find the identities in this using equal error rate. So this whole setup can be simulated using the automatic speaker verification system. When the enrollment data and the test data both are original, then we obtain the baseline equal error rate, and this is what is desired by the attacker, because this is the equal error rate for least privacy protection. Second row indicates the ignorant attacker, which has no knowledge about the anonymization and uses only the original data to conduct the trials over anonymized data. Here, the enrollment and test conditions mismatch, so you may guess that the attacker will perform poorly. But this was the technique which was used to evaluate the privacy protection mechanisms in all the previous papers, all the previous studies. And third is semi-ignorant, where we enable the attacker to also use the anonymization information to transform the enrollment set. Now the enrollment and test conditions will match, and this attacker hence is much stronger than the ignorant one. So we will see these results soon. Now let us look at the utility evaluation. For that purpose, we employ the automatic speech recognition system, where we first decode the original speech and obtain certain word error rate, and then we decode the anonymized speech, and the rise in the word error rate quantifies the loss of utility. Now let us look at the results. The results layout is as follows. Here on the x-axis you can see there are different attackers, and on the y-axis you may notice that it's equal error rate obtained by these attackers. So the goal of the attacker is to obtain a baseline equal error rate. You may already notice that the ignorant attacker performs much poorly than the semi-ignorant one. And I may also say that a higher equal error rate indicates that the attacker is not able to find speaker's identity, and hence it's the target for the higher privacy. And lower equal error rate means lower privacy. So if we look at the first and third group, it indicates the ignorant attacker. The second and fourth group indicates the semi-ignorant attacker. And if you look at the orange bar, which indicates PLDA, you may notice that it performs much better than the cosine measure in terms of the distance metric in X vector space. And for this experiment, we fixed the proximity to far and gender selection to the same gender as the source. Now let us look at the results of proximity. Here you may notice that the in the semi-ignorant case, the purple and the brown bar, which is the sparse and dense regions, perform much better than the rest of the regions. Here we fix the distance to PLDA, and the target gender is same. So we may say that dense and sparse regions are much robust in terms of privacy. Now let us look at the gender selection results. We obtain something interesting here. If you look at the male case, you may notice that when we select the target pseudo speakers from the same gender, then the semi-ignorant attacker performs much better, but the ignorant attacker performs better in case when we select the target pseudo speaker from opposite gender, while the random gender selection maintains the equal error rate in both the cases. Same equal error rate in both the cases. Hence, and this phenomena is also seen in the female case. Hence, we may infer that random gender selection is much stable than same or opposite. Now, let us answer the question which we asked regarding the averaging of X vectors. Does it really produce X vectors or target X vectors which are far from the source after averaging? So on the y-axis, you can see it's minus PLDA. Because PLDA is an affinity metric, we report the minus PLDA as the distance metric. And a higher value in this will indicate that the pseudo speakers are far from the source. Now compare the distance metric, which is cosine and PLDA. We see that the orange bar, which is PLDA, gives us much better, much farther pseudo speakers than the cosine measure. If you compare the different proximity values, you will indeed see that when we want to obtain the far pseudo speakers, that is the highest average distance from the source, and near indeed produces lower values. So the proposition that we conjectured, that averaging might result in a pseudo speaker which is closer to the source, is actually false. And here you may see that in case of gender selection, when we select the pseudo speakers from the same gender, then it results in overall average distance which is quite low, because they are from the same cluster. In opposite, the pseudo speakers are from the opposite, the different gender clusters, so it's quite far, while the pink bar, which is the random, is in between these two. Now let us look at the TSNE representations of the X vector space before and after anonymization. So on the left, you will see the original representation where intragender variance is quite high and genders are also separable. But if you look at if you look at the plots on the right side, the first plot indicates the anonymization, which is produced after random proximity and same gender selection. You will see that the genders get more tightly clustered now, and even the separation between genders has widened. So this is not quite desirable from anonymization perspective. If you look at the second plot, you will notice that it is dense proximity and random gender, and now the genders are inseparable. That may be the reason why dense proximity performs better than rest of the dense proximity and random gender perform better than rest of the design choices. Now, in terms of utility, the highlighted row indicates the baseline word error rate, which is 3 to 4%. And you may notice that rest of the numbers, they climb up to 6 to 7% after anonymization. A good performing sparse proximity raises the word error rate to up to 10%, which is quite unreasonable from the perspective of anonymization. While you can see that the dense proximity and random gender gives us quite reasonable results in terms of utility. Hence, finally, we may conclude that PLDA distance is marginally better than cosine distance in X vector space. And when we map the target pseudo speakers in dense region in combination with random gender selection, we obtain quite reasonable privacy as well as utility. So in terms of future directions, we want to explore much stronger attackers, such as the semi-informed attackers in this diagram. As you can see, the speaker verification system is also retrained using the anonymized speech. This empowers the attacker to make much better discrimination between speaker's identity in X vector space. So it will give us a better benchmark of privacy. More questions that we want to explore are whether the data that we obtained after anonymization, is it suitable for training an ASR model? And the second question that we indicate here is that we do not change the bottleneck features and the pitch. So is there any speaker identity information which is being leaked using these features? So please stay tuned with our upcoming papers to know the answers of these questions. Thank you so much for your attention. Please send your questions and queries on the email that are shown on the screen. Thank you so much.